Hi guys, I'm Su Teng, and welcome to my YouTube channel. Uh, this is this is a channel where I'll be doing some videos to help you learn some of the the JC stuff better. And yeah, so for this video, I'll be covering some. I'll be doing an introduction to calculus. So for my videos, right, it will be slightly different from your it will be slightly different from what you normally learn in your textbooks, in that I'll be using some I'll also be explaining some out of syllabus stuff to help you reinforce your learning. And not only that, right, I'll try to, for all the formulas or whatever stuff, for all the formulas or whatever other stuff you need, I'll try to show you the derivations, or at least show you a method of how to understand these, or at least show you how to understand what is you are supposed to learn. Yeah, so let's start. So let's start with the definite. So for calculus, let's start with the definitions of derivation and integration. For differentiation, the definition is the rate of change of a graph at any given point in time. So let's say you have a graph. Yeah, so the rate of change at this point is basically the gradient here. So this, if this is y, if this is x, then this is the gradient, the derivative of the graph at this point. Then for integration, the definition is the definition is the area under the graph. So for example, if you want to find the area of the under the graph of this area under the area under the graph from A to B, then you have to do integration to find this area. Yeah, so that's the basic definition, which I think you all should know. Now I'll explain some of the terms behind differentiation and integration. Differentiation, as you all know, is dy over dx, which is differentiation is to find the derivative of a graph, basically, yeah. And integration is the integral of fx times dx, fx dx. But here I'll go a step further and explain what exactly are these terms. Why is differentiation dy over dx, and why is integration the integral of this thing? So to start, I'll explain what is dx. What is dx? Dx is basically in a very small quantity of x. By that I mean infinitely small. So that means that, let's say if I draw a graph. So let's say if I draw a graph, then dx would be a super small section of x. Yeah, okay. So dx would be an infinitely small section of x. Then for dy is basically the same thing, where dy is an infinitely small section of y. So that's why dy over dx is the derivative of x at this point. So let me give you some, let me link it to what you already know. So you all know about delta y over delta x, right? Delta y over delta x is is like this. You get given a graph, you are given 2 points. Then you connect the 2 points. Then the horizontal, the difference is x, is your delta x, and the difference in y is your delta y, right? Then delta y over delta x is basically the gradient of this, is basically the gradient of this line. Sorry. Yeah, delta y over delta x. So imagine this. What if you shrink delta x? What if you keep moving this point along the graph and you shrink delta x until it becomes to 0? Then what will the gradient become? So as you can try and imagine it, slowly as you move this point towards the first point, you can see that the gradient will slowly tend towards the tangent to the curve at this point, which is supposed to be the derivative at this point. So essentially what dy dx is symbolizing is dy dx is symbolizing is essentially your delta x, your delta y over delta x as your delta x tends to 0, sort of like a limit. So as delta x tends to 0 but is not exactly 0, then your delta y over delta x will eventually tend to what is dy over dx, which is your derivative. Yeah. So I'm sure you all know the rigor. So the rigor is I'm sure you all know differentiation by first principles, right? Yeah. So that's the rigorous definition of differentiation, which is I'll just write it out. Yeah. So differentiation by first principles is this, as you should know. Yeah. So as you can see, you can imagine it as the bottom part is x plus h minus x, which is also your delta x. Just this time your delta x is your h. Then your fx plus h minus fx is your delta y. Then as delta x tends to 0 or your h tends to 0, then you eventually get the tangent to the graph at x, which is your derivative. Yeah. Now I'll explain integrate the terms behind integration. So integration, as you all know, is this symbol. If you want to integrate fx, then this is how you find the integral. So why is it this thing? Yeah. Why is it this expression? So let me first draw a graph of fx against x. So just assume f is a continuous function. So you already learned that you already learned that dx is represents an infinitely small quantity of x, right? So let's say you want to find the area under the graph here. So what imagine you split it up. So let's try and find an approximation of the area under this graph. Imagine if you, so what we can do is we divide it into rectangles, and each rectangle has a width of delta x. You basically divide something like this. So for each rectangle, the width is delta x, and your height is the value of fx at whatever point that is. So the area is basically the sum of the area of all these rectangles. It's an estimation. So it's the sum of all these rectangles. So you write it as fx times delta x over all these values of x. So let's say you were to shrink the rectangles. You make it slightly smaller. So you shrink dx. You shrink the rectangles. So as you can see, slowly. So now you have a better estimate of the integral of x, right? Since your delta x is now smaller, and so slowly you have a better estimate of, as you shrink the value of delta x, basically you'll slowly get a better estimate of what the area under the graph is. What the area under the graph is. So what if you keep shrinking delta x until it becomes dx? So this is integration. This is how you do your integration. You shrink your delta x until it becomes 0, and then eventually you'll get this. So your delta x becomes dx, since dx is your delta x but infinitely small. Then the summation becomes the integral symbol. So this is what the integral symbol represents. Your integral basically represents a summation. It's just a fancy symbol for summation. So it's a summation of fx times dx over all these values, over the x from all the values of x within this range. Okay. So this is how you sort of derive the expression for integration. So now we have learned about what is differentiation and what is integration. So I'm sure by now all of you should think of differentiation and integration as the opposite of each other, right? For example, if you want to differentiate cosine x, you get minus sine x. But if you want to integrate minus sine x, you get cosine x plus c, where c is some constant. So it's reasonable. By now, I think all of us can think of differentiation and integration as the opposite, as basically the inverse of each other, right? The integration is inverse of differentiation. But just now, look at what I explained just now. Differentiation is given some random graph. Differentiation is the rate of change or gradient at some point in the graph. So it's basically relating the graph to its gradient. But integration is given a graph, you find the area under the graph. So it's basically relating the graph to its area. Okay. So this is differentiation relating the graph to its gradient, and integration relating the graph to the area under the graph. So if you think about it, why is it actually clear or obvious that differentiation and integration are actually the opposite of each other? It's actually not that clear, right? Like this, from the graph you get the gradient. So given the gradient, so the inverse of differentiation is given the gradient, you get the graph. But the integration is given the graph, you find the area. So it's actually not that clear why the inverse of differentiation can be thought of as integration and vice versa. So for this, we actually need a special theorem. You actually need a special theorem that that's not covered in the syllabus. The name of this theorem is the fundamental theorem of calculus. So I'm not going to explain what the fundamental theorem of calculus is here, but what it basically says is that it basically just says differentiation and integration are basically the same thing, and yeah, what it basically says is that if you want to find out more, you can just Google the fundamental theorem of calculus and find out more yourself. I'll not explain it here. So I think that's all for this video. Thank you and bye bye.